Shut up and sit down.
Well, hey everybody, welcome to part 2 of Article 100, where we continue on with understanding the definitions that are involved in the National Electrical Code for the 2020 edition. Definitions are critically important. That's why we're taking the time to go over them. But I'm moving quickly, so I need you to rewatch this video when you need to. And remember, we're not going to cover every single definition. We would be here forever. And I really want to instill in you that we're going to cover the more important ones as part of this program. All right, so let's get into the definitions real quick. And now we come to our first term in this part 2 is cabinet. Real important for you to understand what a cabinet is. A cabinet is an enclosure that is designed for either surface mount or flush mount, and is provided with a frame, mat, or trim at which a swinging door or doors are or can be hung from it. Now, think of a panel in your house. That panel has a panel board, which is the guts. That is covered under UL 67, and that is a definition for panel board. But the fact that it's being installed in a cabinet is a surface mount or a flush mounted enclosure that is designed with a mat or a trim or a frame component that allows you to put a swinging door on it, or that's designed for doors to be hung on it as well. That was its initiated design. Then that's considered a cabinet. Not to be confused with other types of enclosures. Okay? A cabinet is very specific, and the reason that you want to understand the term cabinet is because as you're moving through the NEC, you're going to see the term come up from time to time. And I want to make sure that you understand what a cabinet truly is. Okay? All right, so the other aspect of that is we have rules for cabinets in 312, whereas we don't want you to confuse this with boxes and device boxes that would be in Article 314. Okay? So subtle difference in how you apply them, but understand that it is an enclosure that's specifically designed to be either recessed in a wall or mounted on the surface of a wall, let's say. And I use wall generally, could be on a column or whatever it is, but you get the idea. And it allows other components to be inside of it, okay? But it's designed to have either a door on it that swings or designed to have a door that can be hung from it, okay? It could be totally removed, but it's designed with that intent. That's a cabinet, okay? The next thing is that I find important is we'll talk about what's a charge controller. A charge controller is typically used on a battery system or any other type of energy storage system where you're charging these batteries or charging this system, and you don't want to overcharge the batteries or the energy storage system. So you'll have something that controls the DC voltage or the DC current. It might even control both of those. And it's going to keep your batteries from being overcharged, which ultimately is going to damage the batteries, okay? So sometimes it's part of a wind generation system that has a storage system through inverters, and it stores it as energy. PV systems, the ones that you can get instant gratification from, those have a storage system like batteries, lithium ion, or something like that. And you need a charge controller in the system so that it does not overcharge the battery, okay? Circuit breakers. Now, there's many types of circuit breakers. And we'll see here, there's adjustable, there's instantaneous, there's inverse time, and then there's non-adjustable, okay? And so we'll talk about each one of those quickly. But what is a circuit breaker in general? A circuit breaker is a device designed to open and close circuit non-automatic means first. So that means I can go to it and turn it on and off manually. Just boom, 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 boom. Now, we learned in part 1 that an automatic means that it operates on its own, okay? It doesn't take human intervention. Whereas a circuit breaker has to have the ability to turn it off manually, okay? That is a circuit breaker. However, circuit breakers are also designed to open the circuit automatically on a predetermined overcurrent without damage to the breaker when properly applied within its rating. So you understand the rating of it, the current rating of it, and how you apply it. If it trips off because of an overcurrent condition, it's not going to damage it. It allows it to be reset unlike a fuse, which is all cases with a fuse, it's a one and done scenario, right? So let's talk a little bit about overcurrent. Overcurrent is basically created of three different conditions. You have what's called a short circuit, a ground fault, and an overload, all of which result in an overcurrent condition, a level of current that rises over the rating of the device. So in a short circuit condition, you have a phase to phase, it shorts out, a lot of energy is transmitted, and it allows the breaker to function, to operate. In a ground fault condition, you take any phase conductor, it faults out to the effective ground fault current path, then it causes a big explosion at that point of connection, if you will, that fault point, and it allows the overcurrent device to function, which in this case was a circuit breaker. And then, of course, you have what's called overload. Overload is where you simply just don't take into consideration the amount of loads that you're putting on the circuit, and it just pulls too much current, resulting in an overload condition, which over time will cause the internal circuitry of the circuit breaker to shut down. Okay? All right? Now, let's talk about the different types. We have an adjustable, we have an instantaneous, which sounds just like it's just like it sounds here. We have an inverse time, and we have what's called a non-adjustable. So let's talk a little bit about adjustable. So if I have a circuit breaker, and in the code mentions that it's an adjustable circuit breaker, what it's telling me is that I can set the trip value of that circuit breaker. It's adjustable based on the current or the amount of time it takes it to trip based on a current curve, or maybe it's some mixture of both in its algorithm of how it's adjusted by the manufacturer, okay? And so that is, and it's usually on a predetermined range, and you adjust that range, and then it's set when you adjust it to it that it functions at that value. And that's an adjustable, okay? So anywhere in the code that talks about an adjustable circuit breaker, it's going to have some component in its current rating or its time that can be adjusted or manipulated, okay? Next, instantaneous trip, okay? And again, we're talking about circuit breakers. An instantaneous means that it is tripping, okay, immediately at an indicated term. There is no delay, okay? So when I say instantaneous trip, it gets to a certain value and the breaker is designed to trip off. That's it. No delay. It's not allowing for a certain amount of inrush. Whatever it's set at, that's it. And that's your tripping point, okay? That's instantaneous trip. The next one that we deal with, and probably more often than not, all of the ones that you see in your typical panel for branch circuits and appliances and things like that, is called an inverse time. That means it's inversely proportional. The greater the magnitude, okay, of the current at any instant, okay, then the delay increases. So the more the current, then the time that it reacts is quicker, okay? So let's read it. It says, a qualifying term indicating that there is it's a purposely induce a delay in the tripping action of the circuit breaker, which delay increases as the magnitude of the current increases. So again, very quickly, when we have a lot of current, we have very little current, it's very much delayed. In fact, if it works in its parameters, you're not going to have a problem at all within its ratings or within its range. But if that amount of current increases, say to a short circuit condition, a ground fault condition, okay, then what happens is immediately it's going to be inversely proportional, okay? You with me? It means that that current is so high, the breaker is going to trip really quickly. Let's put it to you this way. If you don't do grounding and bonding properly, and you don't have an effective ground fault current path, and you don't make all those connections right, then when there's a ground fault condition in that circuit, and when it happens, you never know, then what happens is it's not going to have a low impedance ground fault current path back to the source. So we have all that energy that happens at the ground fault, and it can't make its way effectively back to the breaker to recognize it. And because it can't recognize that massive increase in current, then it's slow to trip. Now, if you do everything right, then that massive amount of current that's coming in will cause that breaker to trip very quickly, okay? I mean, very quickly, faster than a blink of an eye. And that is what it's intended to do, okay? So when you hear somebody say it's inversely proportional, that means that the higher the current, the quicker the trip. The lower the current that you have, the longer the delay. Inversely proportional, okay? The next thing that we have is non-adjustable. And again, in circuit breakers, it's exactly how it sounds. It's non-adjustable, okay? It does not have any adjustable to alter the values for the current. It is set to trip, okay? Or has a set time that it's required to operate, and that's it. The reason we talk about each one of these is because you'll have applications in the code, most notably, let's say for motors, when we're dealing with short circuit and ground fault protection, and we're sizing based on table 430.52, which is a result of current values that we're going to get from the FLC, which is in 430.248, 249, and 250 when we're dealing with motors, and we're sizing that short circuit ground fault protection. We need to know whether we're dealing with an inverse time, a time delayed fuse, a non-time delayed fuse, or an instantaneous trip. And the percentage of that FLC value that we base that table on is really dependent on the type of device you're using, what type of circuit breaker or overcurrent protection, such as a fuse. A fuse and a circuit breaker are both overcurrent protective devices, okay? So it really plays a role in that, and you need to understand, if you're dealing with circuit breakers, what the difference of each one of these circuit breakers are. Incidentally, again, me and you, probably on a day-to-day basis, really deal with inverse time, okay? That's the one we mainly deal with, okay? Now, class 1, class 2, class 3 circuits. Now, this is going to seem weird for a second because class 1 circuits are from the portion in the wiring system on the load side of an overcurrent device, or it could be from a power limited supply. And when we say power limited supply, that means that in Article 725, for example, which deals with signaling and control, it's going to tell you, for example, like it says here in the informational note, that if you go to section 41, it's going to tell you what the voltages are for this class 1 application, but it's also going to say, what if you have a power limited source, that what is the maximum power that you can have to supply a class 1 circuit. So that's where you go, and that's why the informational note is here, so that you can go look at that and get a better understanding. Now, we can do that because we can look at 241 and see that it says, then you have a class 1 transformer, okay? It's going to tell you shall comply with part 1 and part 2 of Article 450, which deals with typical transformers, class 1 transformers. Nothing really changes you. However, you'll notice that it says that power limiting aspects of this are very much, for example, 30 volts and 1,000 volt amperes. So whether it's the VA or you're dealing with 30 volts, okay? That is your power limiting. So anything that comes off of a piece of equipment or supply source that is 30 volts or 1,000 VA, okay? That is the output, that is the rating output. Okay, and it can't be more than that when we talk about class 1 power limited circuits. Okay, you with me? All right, so you have all those aspects. Now, other class 1 power sources that you see here that you can follow through and understand that. All right. All right. So let's get back to where we were. All right. Now let's look at class 2. Now, class 2 is typically going to be considered a safe circuit when it comes to fire initiation. It really can't initiate a fire. But a good example of a class 2 would be like a doorbell transformer when you originate that from the secondary side of that doorbell transformer, because leading to the primary side of it, that is normally a branch circuit. But from the secondary side of that is where you're going to initiate a class 2. And it is very safe from ignition, okay? And it's considered safe from electrical shock. But you need to make sure the equipment is listed as class 2 in order to be able to use the benefits that you're going to get in 725, or if you have a piece of equipment that says that you have to only install class 2 circuits. Now, inside of 725, we'll give you the different wire types that you can use and all that type of stuff, but you just need to understand what a class 2 is. It is very power limited, okay, and it is considered safe from fire ignition, and it's considered safe from electrical shock. just like you get on a doorbell. It doesn't mean you can't get a good buzz from it, but it's not typically considered a unsafe condition with it, okay? And there's rules in 725 for Class 2s that you will look at when we get there later on in this series. Now, Class 3 might sound intuitive because at this point, you went from a Class 1, and then you went to a Class 2, which was a little safer. Now you're going to go back up to a Class 3. And a Class 3 is from the load side of a Class 3 power source, whatever that might be, and you're going out to equipment that needs a Class 3 power source. Then it says, due to its power limitations, okay, a Class 3 circuit is considered safety from fire ignition. However, since the higher level of voltage and current than a Class 2 is permitted, additional safeguards are specified to provide protection from electric shock hazard that could be encountered. So, not as intuitive where you think you're going from a 1 to a 2, which is less, down to a 3, which is less. It actually goes the other way. So 3 has a greater risk of shock, obviously, than a Class 2. Okay? So just remember, when you're working with this and you're looking in the code, this should give you the foundation when you're looking at it and you're working on something that you have to deal in a Class 3 circuit, and you say, okay, I got a piece of equipment. It says that it's a Class 3 circuit. That's what the output is, and I'm feeding some piece of equipment from it. Now I'm going to go into 725 and look at all the rules that are associated with a Class 3 circuit. And that gives you now know what it is. It's not going to start a fire, but it is more of a shock hazard than a Class 2. Okay? So, again, you work your way through it, and that helps you understand the basics of it all. Next one we're looking at is clothes closet. Now, you might say, Paul, why in the world are we going to look at clothes closet? Why do I need to know what a clothes closet is? You and me know what a clothes closet is. However, the term closet is used throughout the code, and then clothes closet is also used throughout the code. Most notably in 410 when we're dealing with clothes closets and luminaire applications. Now, in that scenario, we have shelving, we have LEDs, we have incandescents that have to be enclosed, we have fluorescence, and there's spacing and separation from shelves and combustible materials and all that stuff. But that's clothes closets. Now, in a project, I could have an electrical closet. I could have a utility closet. They are distinctly different than a clothes closet. So we need to understand. So we have the definition for clothes closet, and it is a non-habitable room. We also have a definition for what is considered habitable room or habitable space now in the NEC. So that helps us a little bit. Basically, a non-habitable room means I'm not going in there to live. I'm not going in there to spend any time, any significant time, in and out of it. Although we do, again, have a definition of what a habitable room is. That's my layman's term is it's a closet. I'm going there to get something and I'm getting out. I'm not using it for any long-term use other than to store something. All right. So to be a closed closet, it's a space or a non-habitable room intended primarily for storage of garments and apparel. So those are triggers there, garments or apparel. Sorry, I got an itch there. I got to do it. Sorry about that. All right, so that's what a closed closet is. Now let's move into another one that I think is important. Concealed. What is concealed? Now you saw in a previous episode that we talked about something that was considered accessible when it comes to the wiring methods. What's considered accessible and what's not, okay? Now, let's talk concealed. Concealed means rendered inaccessible by a structure or finish of the building. When we say finish, we're talking like gypsum board or some kind of finish. Maybe you're putting a paneling or some kind of what we call shiplap or something. That's a finish, okay? A structure might be something that is, because of it's the way it's designed, there's a structure that means I can no longer get to it. It is considered concealed. Now, this is where an informational note can be very beneficial, because some people will get when it says accessible, and then they get that confused with concealed, whether or not something's concealed. So now I have a raceway that is put inside of a wall, okay? And it is inside the wall, and we're looking at all that. So what does this informational note tell me? It says the wires that are in a raceway that's concealed in a wall, okay, it says wires in a concealed raceway are considered concealed. So the wires that are in the raceway that are in the wall is still considered concealed, even though they may become accessible by withdrawing them. A big difference in this, and I'll go back real quick so we can kind of wrap our head around it. When we're looking at wiring methods, accessible for a wiring method like a raceway would be considered accessible if it's capable of being removed or exposed without damage to the building structure or the finish, or not permanently closed in by the structure or finish of the building. So the raceway that might be above a suspended ceiling is still considered accessible. Then it would not be considered concealed, right? It's kind of how you put these things together and how you work, and it might make the difference in understanding and applying the National Electrical Code, okay? But if I conceal something, even a raceway behind the wall, then it's considered to be concealed as well, okay, for the wires that are in that raceway, okay? Next, we want to look at conductors. We have what's called a bare conductor, we have a covered conductor, and we have an insulated conductor. All right, now, first thing to remember, this doesn't always mean just round conductors like the wires, okay? It didn't make reference to wire here, okay? I can have bus bars that are considered conductors, and they're bare. I can have bus bars that are considered covered. I could have conductors that are considered covered because they're inside of some kind of sheathing. And then I could have insulated conductors, which again is what we're used to seeing. Insulated conductors like our THHN, THWN-2, XHHW-2, all that, that's insulated conductors. So, bare. It's a conductor having no covering or electrical insulation whatsoever. It is literally bare, okay? A covered conductor is a conductor that's encased within material of composition or thickness that is not recognized by the code as an electrical installation. So, SE cable, service entrance cable, that has a bare, let's say an SER, it has a bare equipment grounding connector. It could be insulated, but in this case, let's say it's bare. Well, that equipment grounding conductor is permitted to be in that SER, and it is considered covered, okay? It is a conductor that is covered by a sheathing, and that sheathing is not an insulation. That's a covering, okay? Another example of that might be a bare conductor inside of a tray cable. It is bare, but it is covered because it is inside of a sheathing material. It is encased in it. Another example might be a UFB cable, underground feeder and branch circuit cable. We're very familiar with utilizing that, Article 340. But it typically has a bare equipment ground in there, but it is encased in a material. So in the cable assembly, it's considered covered. Once you strip it off and it's inside of an enclosure, it's considered a bare conductor. So you see how these kind of work together? It's important. Why is this important? Because there are some aspects, for example, when you're dealing with Article 680 for maybe hot tubs that are indoors inside of a building, or maybe portions of a pool wiring system that's inside of a building that allows you to use Chapter 3 wiring methods, which might allow you to use a covered equipment ground rather than an insulated equipment ground. And it's important to you to understand what covered conductors mean. And that's just a great example of that application, okay? All right, so next we have an insulated, and I think that goes without saying. It's a conductor that's encased in a material or composition or thickness that is recognized as electrical insulation. And where is it recognized? In the 2020 National Electrical Code, you get all of those conductor installations that are recognized by the code in 310.4. It used to be 310.104A, now it's 310.4A, okay? Just another change that took place in the 2020 NEC, just relocation a little bit, okay? So that is what's considered an insulated conductor, all right? Now, conduit body. Now we're talking about things like LBs, LRs, LLs, things like that, pulling Ls, all of those things, whereas it's a separate portion of a conduit or tubing system, you come to a point where I have a removable cover so I can get access to the interior of the raceway system, right? It usually takes place or it has to take place at a junction of 2 or more sections, okay? So I might have a conduit body that has 3 inputs, okay? Or might typically an LB, for example, has 2 inputs, but has removable cover, okay? It also can take place at a termination point in a system. Like many times you have a transformer and they bring the raceway to the transformer and it ends in an LB that goes into the actual transformer. So that's an LB or an LR or an LL or whatever you're dealing with, okay? Now, the code makes it real clear, wow, sorry about that. Boxes, no offense anybody, okay? I didn't mean to come out that way. Boxes such as FS and FDs or larger cast and sheet metal boxes are not classified as conduit bodies. They are just specific use boxes, okay? Specific design for a certain use, okay? And we refer to those as FS or FD boxes, all right? So a conduit body has a specific use for a specific application, okay? LB, LR, LLs, things like that. That's what they are. Next, we want to talk about continuous load. What is a continuous load? Not to be confused with continuous duty, which we'll look at a definition here shortly. A continuous load is any load where its maximum current is expected to continue for 3 hours or more. Now, let me use an example. If I have parking lot lighting, or I have a sign, outside sign with lights on a building, and that is going to run more than 3 hours, and whatever the load is of that sign, the wattage is going to be pulling that based on the lamps that are in there continuously for 3 hours or more. It's just going to keep running, and based on the load that's there, it could be 1,000 watts worth of lamps. If that's on, then guess what? That's 1,000 watts at its full maximum current continuously for 3 hours or more. Then I have to take that as a continuous load. That load has its maximum current, that's maximum wattage value in our example, is going to be on for more than 3 hours or more, all night long, okay? Parking lot lighting, it's going to be on all night long, then it's going to be on for 3 hours or more, then that is a fixed load, okay? That is whatever the wattage of that lamp is fixed, and it's going to be continuously drawing that level of current for 3 hours or more, and I have to treat that as a continuous load, okay? Now let's converse that into an example of, let's say, a range. Now people see the range in their house and they think, wow, that's a large amount of current. And if I cook a roast in the oven for 3 hours and 10 minutes, isn't that plausible? Shouldn't that be considered a continuous load? And the reality is absolutely not, because the load cycles. It's never going to pull its maximum current continuously for 3 hours or more. The loads will cycle in and out, and that's what it's designed to do because it's temperature regulated, okay? So that is an example where that's why we don't treat ranges as a continuous load. Now, one last mix into the equation. Where the National Electrical Code tells you something is a continuous load, then you literally take that as a continuous load. An example of that would be a water heater. So when we're sizing branch circuits, the code will tell us in 422 to take that branch circuit as a continuous load for sizing the conductors and everything associated with it, okay? However, when we do load calculations and we're sizing appliances and we treat the water heater as an appliance, we do not take it as a continuous load. We take it at whatever its value is. Because if we do a standard method, when we get 4 or more, we're going to apply a demand factor of 75% to whatever the value is of that water heater. Okay, we get some diversity. All right, so there's things that you think about when you're doing this. If the code tells you that it's continuous load, it doesn't matter whether in your mind you think, is that thing going to run 3 hours or more? It's irrelevant. If the code tells you it's a continuous load, you take it as a continuous load, which usually translate into 125% rating, okay, additional over the value that you're given, whatever the load is, okay? Now, just remember that. It's when the code tells you that. Now, if you have situations where you're going to go to, for example, lighting in a building, then you know that that's going to be on during the day for 3 hours or more. That's a continuous load. Now, the good news for the 2020 code, for commercial buildings, we had a big change in 220.12, which means that I no longer, when I'm using the VA per square foot values for a building to get the general lighting application, I no longer have to take it at 125% because it's already been factored in to my specific VA per square foot. So that just saves you one extra step. But I might have a special piece of equipment that's in that building that does qualify as a continuous load, and I have to take it at that, okay? So remember that. All right, now let's go on to a few more. Cooking unit. Counter-mounted unit. So when we're doing calculations in 220.55 for cooking, countertop mounted cooking units and ranges and all this type of things, I want to know what a counter-mounted cooking unit is. And it is a cooking appliance. Yes, it is appliance. Now, you're not going to count that in the appliances where you get the 4 or more. That's different. It's still an appliance, but you're going to treat that differently. That's a cooking appliance, and it has its own rules that you're going to follow in 220.55 for that, okay? Now, if you're sizing branch circuits to it, it's got its own rules in 210.19 and all that as well for sizing the branch circuit to it. But right now, we just want to know what a counter-mounted cooking unit is, and it's a cooking unit appliance designed for mounting in or on a counter and consisting of one or more heating elements, internal wiring that's internal to itself, and built-in or mountable controls, okay? So it could have the piece that mounts into the counter that has its own controls, or it could be those fancy ones where it has a separate connected unit that actually is tethered to it, and that might have the unit that drops in, and then the controls get mounted over here, and you have to have separate cutouts in the, I don't see a lot of those. Usually they're all together. But it could. Just know that they're intimate together. They work together, and that's considered a counter-mounted cooking unit. Okay, so that's important when you get to 220.55, knowing what it is. Now, selective coordination, or being selective coordination itself. Okay, so selective coordination is the selective coordination. Okay, and why it's like this, who knows? Basically, I guess they don't want people, because this is the same word. I don't see any difference. Is that people refer to this as selective coordination. But we like to do things in this method. I don't know. Okay, anyway, what is it? So in a nutshell, without getting too detailed, selective coordination means in certain areas of the code, selective coordination is required. Okay? And what that means is if I have a main panel and I have a remote distribution panel, and I have equipment downstream, that if I have some kind of overload condition or some kind of incident that happens downstream in that's going to activate an overcurrent protective device, okay, based on maybe something to do with overcurrent condition, that I am going to only trip the closest, most relevant device, and I'm not going to take out the main, because that main gets taken out, it can affect something else in the system. Okay, so a lot of times in the healthcare facilities, they're called for selective coordination. Emergency systems, they call for selective coordination because we want to make sure that we're taking out the device as close as possible to the source of the incident. Okay, so you want to take it out closest to that portion. So what does it say? It says localization of overcurrent condition to restrict outages to the circuit or equipment affected, accomplished by the selection and installation of overcurrent protected devices at their ratings or settings with a full range of available overcurrents. Means that they're going to be able to work. We're not going to limit their range, but they're installed in a system that from overload to the available fault current and for the full range of overcurrent protection operating times associated with those overcurrents. Okay. A lot of words, and I took a break in there, and it might sound confusing. Again, a breaker or overcurrent device has to be able to operate within its range. That's why we buy it. That's why we're using it. We don't want to get slighted, but when we put it in the system, if I have something that happens here at the end where a piece of equipment might be, I want the closest overcurrent protected device to operate and take care of that issue. I don't want the breaker in the panel, the feeder panel to go out. I don't want the breaker at the service to go out. I want it to only affect the application of where the incident originates. And that's why they call it localization. Okay? The last overcurrent device for whatever the equipment is that's having a problem or something in that wiring, I want it to handle it down there. I don't want it to take out the feeders. I don't want to take out the feeder breaker. I don't want it to take out the service disconnect or the feeder that's feeding a panel downstream. I want it to happen at the closest localized point in the system to where the condition takes place. You with me? I can have some very critical things in that feeder panel. I can have some really critical things in the service panel feeding other loads that I can't afford to have taken out. And so I need to isolate it. And that's what selective coordination is all about. Okay? So you have to design the system where it demands it in the National Electrical Code. Wherever it demands it, then I have to provide what's called selective coordination to that structure. Okay? Now, manufacturers, if you contact them and you let them know, they can provide you equipment that's already selectively coordinated. Or you can follow different types of trip curves from a manufacturer or fuse characteristics to actually create your selective coordination, but then usually you're going to have to prove it and show it. I like to let the manufacturer do it, provided you're early enough into the stage when you're ordering your equipment that I can tell them that, look, panel A, B, and C, and D, all the way down to E, has to be selectively coordinated. Make sure you provide me the equipment that can show that selective coordination. And usually the manufacturers, whether it's Eaton, they do a really good job, or Snyder, they will give you that documentation that you can have for the inspector and everything like that. But it depends on where you get into that stage. It's important on how early you get into that. Okay? All right. Copper-clad aluminum conductors are starting to make their way. Now, they've been around for a while. I shouldn't say make their way. But they're fighting very strongly about the expansion of them in the NEC. Me, I just need you to know what it is, because at the end of the day, copper-clad aluminum is still aluminum, okay? When it comes to ampacity values, you're still going to treat it as aluminum. Just because it got a little bit of copper on it, it's still considered aluminum. Now, that's by no means am I talking down to copper-clad aluminum. I'm just saying it is what it is. It is aluminum, okay, with a copper cladding on it, okay? In many cases, it allows you to use terminals that were rated only for copper, but I'm using copper-clad aluminum. It would allow you to get away from making that connection, okay? Because it is copper-to-copper connections. It's not dissimilar metals. Even though it's aluminum, and you're going to limit the current because of its aluminum conductor, you're not going to treat it like copper. There is some advantages to being copper-cladded, okay? So we want to read it because there's very few companies today that make copper-clad aluminum. One that I know of is called Copper Weld, and they do a really good job of making copper-clad aluminum, okay? We just need to understand it is very limited in the NEC. It is pretty much limited to the same type of ampacity values as aluminum, not copper, okay? All right, so what is it? It's conductors that are drawn from a copper-clad aluminum rod. So the actual rod has to have this copper metallurgically bonded to the aluminum core, right, as a rod, and then it gets formed, okay, formed into the conductor, okay? And so it's got to hold that formation. It can't break apart. So that's an interesting metallurgically done process that is very much unique to that design for somebody that has certain patents on that type of design to make that so that when it's drawing it, they don't separate, okay? They're literally metallurgically, I love that word, metallurgically bonded to each other, okay? And it says, where the copper forms a minimum of 10% of the cross-sectional area of a solid conductor or strand of a stranded conductor. So it's got to take up the cross-sectional area, has to have at least make up 10% of that cross-sectional overall area, okay? Whether it's a strand, 10% of that strand's cross-sectional area, or a solid conductor has to make up a minimum of 10%, okay? So it's kind of like a veneer, if you will, going around it. Okay, next thing, cutout boxes. We don't hear this term used an awful lot by people because people don't necessarily understand. They just call them device boxes, junction boxes, whatever. What's a cutout box? It is an enclosure designed for surface mounting. Okay, so there we go. Cutout box is a surface mounted box that has a swinging door or cover secured directly to the telescoping and telescoping with the walls of the enclosure. A great example of a cutout box would be a surface mounted disconnect where that swinging door or cover is secured directly to it and it actually telescopes into it. That is into the walls. That is considered a cutout box. A lot of disconnects are cutout boxes, okay? Basically, cutout box. But it is an enclosure that is specifically designed for surface mounting with a swinging door or cover, okay? You can have a swinging cover that's not necessarily an access door, but it's a swinging cover, like a disconnect, for example, that's surface mounted, and that cover actually telescopes into the walls of the actual kind of come together and overlap and create that enclosure, just like an exterior disconnect. Many 3R type of cutout box disconnects outside, that is a cutout box, for example. Another term that people get confused is called dead front. They use it for a lot of things. What is a dead front? A dead front is without live parts exposed to a person on the operating side of the equipment. So a dead front panel, for example, is a panel that has the inserts that is not going to expose me to live parts, okay? So that means it has a dead front cover, okay? That is what it's doing. It protects me. So I can have equipment, I can even have switch gear that has a dead front on it, okay? That is without live parts that are exposed to a person on the side of the equipment that I actually have to operate, flip switches, crank out. That would be a dead front, okay? It's dead. It's not live. It's not putting me in contact with the live parts when I go to work on a normal trip application. Circuit breaker with the cover that screws on and the breakers stick through, that's a dead front, okay? That's a dead front cover, if you will, okay? Device. What is a device? And again, we're not covering everything, but we're just talking to the main terms. So a device. What is a device? Now, it's a unit of an electrical system other than a conductor that carries or controls electric energy as its primary function. A device. A switch is a device. It carries it and it controls it, turns it on and off. A receptacle. It's a device. It carries it. Now, it doesn't control it, but it carries it, all right? And that's its primary function, to carry the current so that we can utilize it, so we can get to it on the point on the outlet system, okay? Now, remember, a receptacle is a device. A box that the receptacle goes into is an outlet box. An outlet is a point on the system where I take power from it, whether it's hardwired to a box or a receptacle goes in that outlet box, okay? So don't think of a receptacle as an outlet. And people do that all the time. How many outlets you got? I got 1, 2, 3, 4 outlets. Okay, slang, but I'm teaching you to understand terminologies. It's a receptacle outlet, not necessarily just an outlet, okay? It's a receptacle outlet. And the receptacle itself is a device. You with me? Okay, all right? Now, I can have an outlet box or receptacle outlet box. So that is a receptacle that is an outlet. I'm taking power from it, that a receptacle device goes into it, okay? All right. Next, we all know what a disconnection means is. So when we're looking through the code and we see the term disconnection means, basically, it allows me to disconnect the circuit conductors from its source of power. The disconnect outside for an HVAC unit, literally disconnect the power, okay? The disconnect at the main breaker in a panel, if that's your main disconnection means, I disconnect it from the conductors. I disconnect it, okay? That is a disconnection means. Now, we have different types of disconnect. We have a service disconnection mean, for example, that's using the service. Then we have downstream Disconnection means is a general term. Okay, what can that be? It can be a device or group of devices. A circuit breaker is a device because it does control electric energy, but it can also serve as a disconnection means, obviously. Okay, but it doesn't have to be a circuit breaker. It could be a utilization equipment with an enclosure, maybe a cutout box with a pullout. Okay, and so that is something that allows to be able to use that as a disconnection means. Okay, all right. Some of these are self-explanatory and you can read them, so I just kind of go through them. Next one we'll look at is continuous duty, not to be confused with continuous load. So if I see this and I'm learning, I'm like, when I see continuous duty, I know that I'm dealing with something different. Okay, something that's rated continuous duty means it's operating at a substantially constant load for an indefinite long time, an indefinitely long time. So it is, motors typically, for example, are rated in continuous duty because we just don't know how long it's going to run, and that motor could run for an indefinitely long time. So it has a rating that is considered continuous duty. Now, you've got other motors that are not continuous duty because they're going to be time specific, okay? And that's when we look at these. And most motors, by the way, are going to be treated as continuous duty, which ultimately is going to translate in the code as dealing with 125% as a factor that you have to take into consideration because of continuous duty rating. Don't get that confused with continuous load, even though it seems to seem similar. If you want to remember the 125% for all continuous duty motors, that's fine, but understand that continuous load is totally different than continuous duty, even though they do share the same multiplier. Okay. Next, we have intermittent duty, periodic duty, short time duty, and varying duty. And each one of these will come into play if you ever deal with things like escalators, elevators, dumbwaiters, because it's operating for a specific burst of time, but not constantly all the time. Okay? So, intermittent duty means operation for alternate intervals of one load and no load, on and off, or two, load and rest, or three, load, no load, and rest. Okay? That would be considered an intermittent duty. Now, what's important by this is when you're dealing with the load and you're in the National Electrical Code under Article 430, if you're getting into this and you're sizing conductors and everything for intermediate, periodic, short time, and all that, you're going to look at 430.22e, which is telling you to use a nameplate rather than what we're used to when it comes to the FLC. Don't worry, we'll cover all that. Don't let your brain wander at this point. I just need you to remember that in 430, there's going to be applications where you're going to need to know the difference between all these. So if it's a load and then no load, or a load happens and then it rests, or if there's a load, no load, and then it rests, or whatnot, then it's going to be considered intermittent duty. You don't make that decision. The design or the condition will make that decision. Whatever it is, if it's an escalator, if it's an elevator, then there's going to be certain rules within the standard for those things that'll tell you whether this motor is intermittent duty, continuous duty, periodic duty, and that'll be the type of motor they utilize. Me as an electrician, I'm just going to wire it based on what type it is, okay? Now, a short time duty, again, operates at a substantially constant load for a short and definite specific time. Means it's very specific. Certain amount of time, it's very short, but it's on, and I'm defining it, okay? It's a definite amount of time. You might have different types of loads, motors, that are going to be short duty. It's very specific. So that would be a short duty, okay? Short and definite specific amount of time, okay? And then you have what's called varying duty. Okay, operates the load and for intervals of time, both of which may be subject to a wide variation. Okay, so back and forth, 10 minutes, 5 minutes, 3 minutes, 10 minutes, whatever it might be. Okay, it's going to operate a certain load and a certain amount of time, and they could vary. Okay, the load could vary and the time could vary. Right, and that is considered a varying duty motor. Okay, or you'll see most often than not, a motor is going to have a varying duty value on it. Okay, now you'll notice this doesn't specifically say motors. So anywhere in the code that it makes reference, I'm telling you that 99% of the time you see these associated with motors. But again, whenever you see the value, be very aware of what it's talking about. Okay. One family dwelling, two family dwelling, multi-family dwelling, and dwelling units. Okay. Significant when we're doing things like calculations and we're doing a single family like probably what you and I live in, or a two family like a duplex application, or a multi-family where we have three or more specific dwelling units. Then it's important because we're doing calculations in 220. We need to know, because if I'm using an optional method where I'm going to have three or more, then I want to be able to use 220.82. I want to be able to use that optional method. And so we might be doing a standard method for a one-family dwelling unit. Okay, so important to understand these terminologies. One-family dwelling is a building that consists solely of just one dwelling unit. A two-family dwelling is a building that consists solely of two dwelling units in the building. So in this case, a great example is a duplex. Okay, it's one building, but it's probably separated by a rated assembly. If it's an over and under, that's not a firewall, obviously, because it's horizontal, but that is a two-family building. Okay, and again, I could have one building that has a firewall between it, and those two are treated as two separate dwellings. See the importance of knowing what a building is? Because it says a building. Well, we got to know what a building is in order to apply this. Okay? All right. And then, of course, the multifamily is a building that contains three or more dwelling units. So that could be a high-rise building that is a multifamily that has dwelling units in it, multiple dwelling units, apartments maybe, and they're all separated by rated assemblies. So overall, it's one building shell, but you have what's called multifamily dwellings that are inside of it. Three or more will constitute a multifamily dwelling. Real important when we're doing calculations and understanding the difference. Also real important when we're doing things like receptacles, maybe outside receptacles where dwelling units have to have them in the front and the back. Okay, whereas you might have multifamilies, for example, that might only have to have it at the ground floor. And so and maybe only the front has to have it. So important to understand what a one family is, what a two family is, and what a multi-family is. Really important. Now, with that said, we also need to understand what a dwelling unit is, because we have one family dwellings, two family dwellings, multi-family dwellings, and it might reference that in the code. But you know what? You might have application where it just simply references a dwelling unit, and it might be the independent single individual dwelling unit. Okay, so it says a single unit providing complete and independent living facilities for one or more persons, including permanent provisions for living, sleeping, cooking, and sanitation. Real important, because I might have an application where I have an apartment in a multifamily dwelling. So the open space in that dwelling, all this common area, are treated, for example, as a commercial space. But then each individual dwelling unit in the code can be treated individually when we're doing load calculations for that individual dwelling unit. Okay? And then I have calculations that I would do, let's say, for the service, which is probably dealing with the entire facility, which might be a multi-family building where you have three or more dwelling units. So you have the status, if you will, of the dwelling, and then you have the specific status of the individual unit within that dwelling. Okay? So in order to qualify as a dwelling unit, then it has to have the four elements. We have to have the living, we have to have the sleeping, we have to have the cooking, and we have to have sanitation. In layman's terms, living room area or living space, bedroom with sleeping space, cooking space, kitchen, and sanitation. Now be careful, and sometimes you have efficiencies which might not qualify as a dwelling unit because it doesn't have all these elements involved. But you could have a living space that is also meeting the requirement as a sleeping space, okay? And you have a cooking space, and you have beds, so it would be a dwelling unit. Now, you might have an application where I have a mobile home, hotel or motel suite that has all the elements in it to make it treated like a dwelling unit because it has cooking, sleeping, sanitation, and living and all that type of stuff. So that's why it's so important to define what's a dwelling unit and what's not. And why else is it important? Because once we establish it's a dwelling unit, then we have certain rules that we have to meet for spacing of receptacles and all that type of thing like we do in a normal house under 210.52. Okay? So that's why it's so important to break it down and understand what it is. Okay? It'll serve you well also as you start looking at other articles in the code and they make reference to one family, two family, multifamily, or even dwelling unit, which is a specific unit. Then you can go, I get it. I understand it. It's all clear. So that's important. The next thing we look at is what's called an effective ground fault current path. That is why we're tying all metal parts together. That's why we're making sure that the equipment grounding conductors are done, they're installed correctly, all of that because we're trying to create an effective ground fault current path in order to facilitate the operation of an overcurrent protective device. And that's basically in a nutshell what it says. It says an intentionally constructed. When I say intentionally, there's a reason why you're tying all those equipment grounds together. There's a reason why you're bonding metal parts together that are part of the grounding electrode, equipment grounding conductor path. There's a reason what we do in Article 250, and that is to create an effective ground fault current path. So it's an intentionally constructed, means you got to make it, low impedance electrically conductive path designed and intended to carry current under a ground fault condition from the point of the ground fault, wherever it is in the system, wherever that incident takes place, to the electrical supply source, and that facilitates the operation of the overcurrent protective device or ground fault detectors. Okay, so you could have, for example, an ungrounded system versus a normally grounded system like an AC system. You could have an ungrounded system. And if you have that, you have what's called ground fault detectors. You still got to have an equipment grounding conductor path, okay? Even though you don't have a grounded conductor on the load side of this ungrounded system, it still has to have an effective ground fault current path, okay, in case the metal parts get energized. And you have to establish that effective low impedance electrically conductive path. And so that's why we tie everything together. That's why we'd use different things like the supply side bonding jumpers from the secondary of the transformer to the panel, or we make sure that we run all of the equipment grounds that we run and tie everything together and bond everything. If we have raceways that are being used as equipment grounding conductor, that we make sure everything's connected together to establish an intended, purposely constructed low impedance electrically conductive path. And that's why we're doing it. It's a safety system. It's all intended to remove that breaker really quickly. Because if you don't, and you get locked on it, there's a hazard that's there. Okay? Electric vehicle. We probably all know what an electric vehicle is, EV. There's different types of electric vehicles. There's plug-in hybrids. We call them PHEVs. And basically they just plug into the system. People are familiar with the Teslas, the Volt from Chevy Volt, the all-electric car, EV car from Nissan is called the Leaf, things like that. But there is other types of EV vehicles. There's EV tractors, okay, things like that. So let's read it. It says an automotive type vehicle for on-road use, such as passenger automobiles, buses, trucks, vans, neighborhood electric vehicles, electric motorcycles, and the like, primarily powered by electric motor that draws current from a rechargeable storage battery, fuel cell, photo array, or other source of energy. Okay, so that's what an EV vehicle is. It says plug-in hybrid electric vehicles are electrical vehicles having a second source of motive power. Okay, so plug-in hybrids typically will plug it in, but they also have a second source like gas or something like that. Whereas you have all EV vehicles are available as well. Tesla is an all EV vehicle. A Leaf is an all EV vehicle. A Volt, for example, is a PHEV. Okay, it has another power source, which is a motor there. Okay, so that's a plug-in hybrid as well. It says off-road, self-propelled, electric, mobile equipment such as industrial trucks, hoists, lifts, transports, golf carts, airline ground support equipment that runs around, that actually pulls the aircraft around on the tarmac and things like that. Tractors, boats, and the like are not considered electric vehicles. Okay, now they might be electric storage components that are going to tie into a system, but that's not what we're trying to convey as electric vehicles. So again, you might have electric boats, you might have electric tractors, like I said earlier, you might have electric golf carts, a little things like that. But, okay, those are different than those neighborhood electric vehicles that you see people riding around in these resorts and things like that, okay? Totally, totally different. And also, those aren't golf carts. Those neighborhood electric vehicles are literally designed like little automobiles, okay? They're not golf carts. Golf carts are not EV vehicles, okay? All right, just so you kind of understand the difference. The next thing, and these are also pretty self-explanatory. So let's talk about something that's considered enclosed. When we have things that are considered enclosed, it's real important that we understand what enclosed means. It says, if something's enclosed, then it's surrounded by a case, a housing, a fence, or a wall. And what is it doing? It's preventing me and you from accidentally contacting energized parts. So anytime that we see in the code that says something is enclosed, means that it is literally surrounded by either a case, a housing, a fence, a wall that's preventing me from accidentally coming in contact with energized parts. So remember, when we see the word enclosed, what we're saying, we're creating this barrier from potential live parts here, okay? That's what enclosed means. So enclosed means the electrical component is enclosed within a housing, a case, a fence, or a wall, okay? A case can be very broad, okay? So for example, in a transformer, the windings and everything is enclosed behind a housing or enclosed behind a case, if you will. So the windings are enclosed. And the reason they're enclosed is so that I don't accidentally come in contact with those energized parts. Makes sense? All right. Now, what's an enclosure? Because we see that being utilized a lot. Okay, you saw it before as a cutout box is a type of enclosure. Cabinet is a type of enclosure. What in the world is an enclosure? It is a case. See what's in case? So a panel board, which is the guts, inside of a cabinet, which is an enclosure, is what? It's enclosed inside of the enclosure, which is also a case. I'm serious. Just the way, if you look at it that way, you start to understand. You get it. Panel boards, the guts, it's in a cabinet. I got it. When it's in that cabinet and everything's on it with a dead front cover, now it's what? It's enclosed inside of a cabinet, which is also an enclosure. And that enclosure is a case that's enclosing the panel board. Wow. If your head just go, your head just blew off. Because you're now starting to get to that level where you're like, I knew what it was and I knew it, but now I'm getting it, right? You're like, I get it. I feel it. Okay. The next thing is energized. Electrically connected to or is a source of voltage. So if I'm connected to something and those conductors are hot or live, they're considered energized. When I power a transformer, that is considered, once the power's on, the supply, the primary side disconnection mean is on and everything's good, then it is energized, okay? It is a source of voltage, which is, voltage is pressure. Now, you might not necessarily have any current because there's no load until you come in contact with it and you become a load, but you're contacting energized live parts, okay? Keep that in mind. Now, another definition, equipment, very broad term in the NEC. This is something that you want to really remember because throughout things like Article 680, dealing with swimming pools, hot tubs, spas, it makes a lot of references to equipment, especially when we're doing equipotential bonding in 680.26. It'll talk about equipment, equipment, equipment. What is equipment? And all through the code, it makes references to equipment. We need to know what equipment is because some rules hinge on equipment. And what is it? It's a general term. It includes fittings, couplings, connectors. Those fittings are equipment, electrical equipment, okay? Devices, switches, circuit breakers, receptacles, all of that is considered equipment. Appliances are considered equipment. Luminaires, equipment. Any apparatus that's associated with luminaires or other equipment or other components, the apparatus is considered equipment. Machinery that is connected to the electrical energized circuit is equipment and the like used as part of or in conjunction with an electrical installation. All of that, okay? Raceways, they're part of or in conjunction with, right? They are considered apparatus that uses fittings that can connect together to make a complete system. They are part of an electrical installation. That's all equipment. Really important to know that when I'm reading the code and I see them reference something about a specific rule that deals with electrical equipment. Make sure that you understand that. All right, electrical potential, equipotential plane. Now, we utilize this in a couple areas. We have electrical equipotential planes that we utilize, for example, in swimming pool applications around the perimeters. We have it also when we're dealing with agricultural buildings, and we're trying to establish equipotential plane. What is it? It's accessible conductive parts bonded together to reduce voltage gradients in a designated area. So when the cows come up the ramp into the milking house, and because there could be differences of potential, of gradient potential that the cow, and they can feel very sensitive voltage gradients, okay? Then what happens is, what we're doing is we're masking everything as they enter into it so that there is actually reducing the voltage gradients, okay? We're reducing the voltage gradients from what might have been a higher level to a reduced level so that the cows don't feel the difference. Okay, so moving to swimming pools, we're reducing the voltage gradients between two touch points so that when I'm stepping out of the pool that I don't feel this great vast gradients that I'm going to get a shock from it. Okay, so we're basically creating an equipotential plane to mask the differences of potentials through a voltage gradient across the surface plane. Okay, so anyway, when we deal with equipotential plane in different areas of the code, you'll get a better understanding of what we're trying to do, what we're trying to achieve. Okay, next, exposed. Now we're talking about live parts here. That means somebody leaves some parts of equipment exposed and they're live. Okay, in a panel, the main lugs from a service, they're live. Now, good news today is that now we have requirements to thermally isolate those live parts. But what is our exposed live parts? And sometimes we can't put a barrier. I mean, it's just going to have exposed live parts. So it's going to tell us that we got to do something. So here's what it says. What are exposed live parts? Those that are capable of being inadvertently touched or approached nearer than a safe distance by a person. Another thing is when we're looking at working clearances and distance between live parts in 110.26, we have to understand that there's going to be distances that we have to separate between live parts for working distances. 3 feet, 3.5 feet, 4 feet, depending on the voltages. So it's really important to understand what an exposed live part is, okay, when it comes to live parts. So here, it says an informational note that says, look, the term applies to parts that are not guarded, isolated, or insulated. They're just live parts, live bus bars that are maybe not required to be insulated, but are definitely live, okay? And you could have inadvertent contact with it, then that's considered exposed. So anywhere we talk about that in the code where it makes a reference to exposed, we're talking about, in this case, exposed live parts. And then that's going to have something else that we have to do to it when it comes to those live parts. Now, what about exposed when it comes to wiring methods? A little different. Wiring methods, when it comes, this is live parts exposure. Now, when it says exposed, and we're talking about wiring methods that are exposed, maybe they're exposed to something like physical damage or not, then it says, look, on or attached to the surface or behind panels designed to allow access. Okay, so if I have wiring method that is behind a specific panel that allows me to get access, then they're considered exposed, okay? Then I can get to them. Another thing is I might have a wiring method that's above a suspended ceiling that allows me to remove a panel to get to it, then they're considered exposed and I can get to it, okay? It allows me specific access, okay? Those kind of concepts. Pretty simple to understand. This is the one that's going to cause you some serious pain. This is the one that's just allowing you to whether or not you consider a specific wiring method or not behind some kind of access panel to be considered exposed, okay? And now that's pretty much where we're going to let off in this unit. Hopefully you got something out of that. You found that it was important for you to get that information. And so I'm excited where we're at. I'm excited about what we're learning. So stay tuned as we move into part 3, and we're going to talk about more definitions. Till next time, stay safe.
Shut up and sit down.